All right, hello everyone. My name is Mike Goelzer. I'm from Protocol Labs. We're the folks who do Filecoin. That's what we're best known for, and IPFS. However, I am not going to talk about those today. What I'm going to talk about is the project I work on, which is libp2p. I'm the project lead for it. I'm sort of the manager of the PL team, which in turn coordinates a lot with a community that's actually much larger than the group that we directly employ to work on libp2p. Let me just give you a little context about why this is part of .day. Basically, Polkadot runs on top of libp2p sort of indirectly. I believe, if I understand correctly, the Polkadot runtime is built on top of Substrate or incorporates elements of Substrate, and which is, I think, it's fair to say is that Web3's sort of vision for what the future of the internet could look like, or at least the blockchain crypto internet. And so we're the networking layer of Substrate. So I think in the beginning, Ashley or someone was talking about, you're going to hear a lot about Polkadot and things built on top of it. We're a thing that's built underneath it. And we provide the peer-to-peer networking layer that allows different nodes to connect to each other and exchange data. So what I'm going to try to do is just talk about the project generally, but with a little bit of a focus toward what I think people here will be interested in. And then I'm going to try to wrap up at like 20 minutes. I have 30 total, so then we can take some questions. I'll do the best I can. I'm going to cut some stuff from the end. Okay, I always like to start with this slide just as a kind of a reminder of where the internet came from. The internet was originally, or what we today call the internet, arose out of research that was done in the 1950s, 1960s in the US and the UK. And the goal of that research was to try to figure out, is it possible to build a communications network that is so decentralized it could survive nuclear war? So you could have in major cities in the US, for example, completely wiped out, and you could still have communication between all of the parts of the country or other countries that were not affected by the war, at least not initially, and that would allow them to, you know, form a resistance or whatever the scenario called for. So this is important, though, because when you look at the internet today, what we basically have are a lot of centralized services. And these are apps that we know and love. Like, I use many of these apps, and you probably do too. And they're all built on centralized models. And the reason for that is quite simple. It's vastly, vastly cheaper and more efficient. And I think that's something that is not popular in the decentralized crowd, but at the same time, if we don't acknowledge it, we're never going to be able to sort of have an answer for it. And so anyway, this is something worth pointing out, that the internet has gone in a much different direction than we had originally intended. So on the subject of peer-to-peer, obviously a lot of people have become very interested in this recently with blockchains, decentralization. There were earlier efforts at building peer-to-peer systems. Some of you, if you were alive in the 1990s or early 2000s, you may remember some of these services. There were file sharing. It was big to share MP3 files back then. And there was also a lot of research into, oh, sorry, I should be pointing the other way. There was also a lot of research into how to do these things efficiently. So Kademlia, for example, is probably the most popular and well-known distributed hash table algorithm, which many of these systems relied on. And so here's how libp2p differs from those things. First, libp2p is a general purpose library built from composable building blocks. So I'll go through what some of those building blocks are later, but we're not focused on any single use case. What we're focused on is enabling peer-to-peer apps generally, both blockchains, and we have a lot of users who are completely non-blockchain. And we're a pure open source project. We're not, it's not something that you buy, it's something that you vendor into your code and hopefully contribute back to. I would also just mention, like, we're not focused on the anonymous file sharing thing. So if you want that, go to BitTorrent. That's not what we're about. And we are very interested in interoperability between different kinds of devices. We've had a lot of success in the last year in getting more people interested in this project, which has been a really cool experience. There's been a lot of organic growth in the community. I just put up, this is the kind of graph you show to your investors, so I'm not going to bombard you with these. I'll just show you one. But this is just GitHub activity. This is like unique users on GitHub, opening PRs, issues, just any interaction with our repos. And it's going up and to the right. So venture capitalists love to see that. So now let's talk about some people who are adopting. So obviously Polkadot, that's why I'm here today. Substrate, it's the lower level. Ethereum 2.0 has just, they've committed to adopting libp2p in Ethereum 2.0. And they've just now gotten to the point where I think there are nodes on the testnet that are running purely on libp2p. So they have another library that is much more stripped down that they use to just get nodes like up and communicating. It's just a basic wrapper around like TCP connections. But I think they finally gotten libp2p integrated into the Ethereum 2.0 nodes. Another one is MetaMask. Most people in this room probably know that. It's a browser extension and a crypto wallet. OpenBazaar, it's like a decentralized eBay. Filecoin and IPFS are Protocol Labs projects, so of course we're eating our own dog food. And there are a lot more, but I'm not going to list them because that would be, it would take all day and it would be silly. So the point is we have good adoption. Now, let me talk about libp2p is implemented in a variety of different languages, and what we aspire to be actually is not a library, but a specification for how to build interoperable libraries in different languages on different platforms where this interoperability facilitates different peers being able to communicate with each other. So originally, there was JS libp2p and Go libp2p. Those were developed by Protocol Labs. Then Parity came along and wanted to use libp2p for various purposes internally, but including Polkadot. And so they developed Rust libp2p. More recently, there's a group of students at UPenn who are building a Pi libp2p. And then in the bottom left, sorry, I didn't have room for any more screenshots, but I want to tell you that there are even more language implementations emerging right now. There are two JVM implementations. One is pure Java, the other is Kotlin. So if you're tapped into the Java world, Java and Kotlin are kind of rivals. Kotlin is like, they both compile down to JVM bytecode, but Kotlin is sort of meant to be the language that you wish Java was. So I'm not a partisan on that. I just, that's my understanding of Kotlin's goals. So I hope I didn't offend anyone. And then C++, which will be great. It'll be a great complement to Rust. Obviously, language that's can be implemented very efficiently. That's so these are the repos you would go to on GitHub, libp2p/rust libp2p, libp2p/go libp2p. You would just go to those repos on GitHub. The C++ implementation, I thought people out here might be more interested in it, so I just point out that you go to Seramitsu, which is a company in Tokyo that's building this, and it's called Kagome. So that's where it is. If it sort of reaches maturity, then it would get incorporated into the libp2p org, assuming that they want to do that. Okay, let me talk a little bit about what libp2p is, and I just want to check the time. Okay. So as I mentioned, we have multiple interoperable language implementations. We're not tailored toward a specific use case, whether it's file sharing or anything else. We're a peer-to-peer library that is intended to be, sort of very modular and very adaptable to different circumstances. So you can use it for a lot of different things. We also like to use it as a platform for to implement new ideas. So Quick, for example, this is a UDP-based protocol that Google invented for to speed up communication with Chrome. So UDP is very fast, but the drawback is there's no concept of connections. It's just like fire and forget and hope that some of the packets arrive. So this is something we've recently implemented into Go, libp2p, and we're working on it in JavaScript. One of the key concepts is that peers are identified not by their location on the network, like an IP address or something, but rather by their public key or a hash of their public key. And so you can have peers showing up at multiple places on the network. Like my phone, for example, is on Korea Telecom's network over IP, so it has an IP address. It's on Bluetooth. That's a name that you can probably see if you do scan for Bluetooth right now. It's on Wi-Fi locally here. So the point is it has a lot of different connections to various networks, and but it has a single unique identity. It's a single phone, and so that is a key part of what we're trying to do with libp2p. And the last thing is something called connectivity magic. That's just what we call it. Basically, we're trying to make connectivity very simple. So a lot of the things that you would have to deal with if you wrote your own peer-to-peer library, we've done those for you, and we've encapsulated them behind abstractions. A good example is a connection multiplexing, stream multiplexing. So within a connection, we allow for multiple streams. All of the multiplexing and other things that are usually painful to implement are done for you by the library. Protocol negotiation, encryption, authentication. Again, these are all things that we do internally in the library. I just want to talk a little bit about what I mean when I say libp2p is modular. So we have these various building blocks, and I'm going to come back to these in a second, talk a little bit more about what they are. But we have these various building blocks. They're abstractions within the library, and what we do is we let you put them together in sort of whatever fashion you want to kind of create your own libp2p that's suitable for your application. So if you don't need NAT traversal, you don't have to compile it in. If you don't need something else, you don't have to include it. But we offer you a lot of different options, and the community offers even more options beyond just what just the ones we offer. Oops. Okay. So let me just try to give a brief sense of what these abstractions are. I recommend, if you want to get seriously into libp2p, you should probably read our documentation in addition to watching this brilliant talk. But I'll just try to give you a taste for kind of how we think about the internet and connectivity. We have an abstraction called transports, which are fundamentally the lowest level of connectivity. They're like there's a TCP transport. There are various UDP transports. As an April Fool's joke, we announced a carrier pigeon transport. That doesn't actually exist, but it illustrates that transports are, it's a very abstract interface, and if you can implement something that conforms to it, we really don't care how you're moving the packets around behind the scenes. Let me talk about content routing. So we have a distributed hash table, which drives several of the things here, including peer routing and peer discovery. A distributed hash table is a data structure. I think most people would probably know this, but it's a data structure that that basically is a hash table, and so you look up keys and you get back values, but it's distributed across many machines, and we use Kademlia, and you can read more about that in our documentation or in the Kademlia paper. Crypto channels, so we will automatically, once you establish a connection to another peer, we will automatically update it, upgrade it is the terminology we use, to an encrypted connection by doing, Diffie-Hellman and establishing a secret key shared between the two sides of the connection. You don't have to do any of this on your own. It happens automatically. If you really want a plain text connection, you can not do this, like you can disable this. So again, a lot of flexibility, but I think in most cases people want encrypted connections. Record stores, again, that's about the DHT. We have a very versatile distributed hash table that lets you store different kinds of data, including arbitrary records. and NAT traversal is something we're working on and developing right now. We have, it's a tough problem. Most machines are behind NAT. In fact, everyone who's connected to the Wi-Fi in here is probably behind some kind of NAT from those routers that we're connected to. And the reality is most outside of servers that have, in data centers, virtually everyone is behind NAT. So there are various techniques to punch holes in NATs, and I'm not going to go into them now, but we support some of them, and other ones we're trying to build out more. I can talk more in detail if there's questions about that, but the bottom line is one of the goals of libp2p is to make it easy to bust through a NAT if you're behind one. I'm going to go through this really quickly. Let me just check the time again. Yeah, so libp2p has a fundamentally different approach to networking than the OSI model that folks learn about in school. So the first problem is the OSI model doesn't really represent how the internet works. So then people came up with a TCPIP model, which is sort of shows that some of the layers in the OSI model are really one thing. And then an even better, I think, or more accurate version of it is this on the right-hand side, the TCPIP protocol suite, where you have a variety of protocols that are basically sitting on top of TCP and IP, and you have some additional stuff inside IP that is not normally discussed in the simple textbook explanation. And then you have the kind of what I would call the hardware layer, like what is the Ethernet router doing when you plug it into a switch? How are they communicating? So this is a little bit more of a nuanced view, but even just going back to the simple view, we don't like it for a couple of reasons. First, by breaking things down into layers like this, it makes it conceptually simpler to implement because I don't have to worry about, I only worry about the layer below me and the layer above me. To implement one of these, I don't have to worry about what's going on 3 layers down. But that creates inefficiency and duplicated effort because if you look at how a typical corporate VPN works, what you see is there's encryption at the I think it would be the network layer, so that's like IPsec. Then there's re-encryption at the I believe it would be the transport layer, so that's like the VPN itself. If it's not an IPsec VPN, will re-encrypt. And then there's again encryption at the top layer when you connect to a website that starts with HTTPS, which is virtually every website now. So it's like you're doing this operation 3 times. It's a relatively expensive operation, and it's only because the application layer doesn't know that there's already been encryption. So it's got to assume, and there's other reasons, but I'm not going to go into them. But so we have a different take on networking, which is represented here. We think that building blocks of the stack should cross these different layers, or be free to cross different layers in the OSI model, and really be based more on what they're trying to do rather than rigidly conforming to this model. I deleted a few slides in here, but basically what I want to convey in this part is that libp2p runs in the browser because of JS libp2p, and that is really cool because it works in mobile browsers too. So it's very hard in the sandbox environment of a mobile browser to establish peer-to-peer connections with other nodes. We have partially solved this, and we are in the process of more fully solving it with WebRTC and other tricks like that. But this is really cool, right? Because my phone can be a full peer on the network in the same way that your more powerful laptop could be, or a more powerful server could be. And other than the performance differences, you really can't tell what's going on. So yeah, we have a huge community. I think I talked about this earlier. And I would love for you to come join us. So let me look at the time. Okay, yeah, this is where I was going to pause. If you Google for my name and then ETHCC, you'll see roughly this presentation, but there's a code demo at the end. I had an hour in that slot, so if you really want to get technically into this project, that would be a good demo to look at. And We have a site, docs.libp2p.io. You can also go to libp2p.io and see various videos. And we're trying to pump out just more and more documentation. It's a big push for us right now to make things easier for new people. So, but that's where I'm going to stop for today. And I would like to use the remaining time for any questions. Yes? Yeah. Okay, great question. So what he's asking is twofold. First, what is the status of the Python implementation? Is it finished? And then secondly, if it's not, what is the best language for a new person to use? So on the Python implementation, it's a work in progress. Basically, this team, the students at UPenn, I think I mentioned, they got a grant from the Ethereum Foundation. They're supposed to finish the project by the end of this academic year, which would be like May or June. Whenever their school graduates. So they're not finished yet. It's not, libp2p is not fully implemented yet. I would recommend the Go implementation. Basically, we've come to treat Go libp2p as kind of the reference implementation, meaning that when we have a specs repo, but it's right now it's rather incomplete. And so when the specs repo doesn't answer a specific question about how to do something, we just tell people, go to the Go implementation, that's canonical, do whatever it's doing. And unfortunately, that causes people to duplicate some bugs that are in the Go implementation, but at least they're compatible with Go. So that's what I would recommend. It's the most mature, and the examples are most mature, and the docs are fairly mature. Anyone else? Okay, well, thank you for your time. I hope you enjoyed it.